All right, 814, compound events. And we're going to be covering two different types of events today. Independent events, dependent events. We'll talk about how they're different. We're also going to be making tree diagrams today. That takes a little bit of time to do. And we're also going to get introduced to the counting principle. We did not cover that last year, so that's a new thing. In a sense, it will begin to replace some of the tree diagram work that we did last year. When you did probability, you built tree diagrams for everything. And again, you'll continue to make some tree diagrams. You'll have to require to make at least one on your quiz, test, stuff like that. So you'll need to know how to make a tree diagram. We'll talk about what the benefits are of tree diagrams, what the downsides are. Where counting principle can come into play and make your life a little easier sometimes. So, yeah, I got it down. Compound events. When we did 813 here, these were just singular events. I said, what's the probability if I roll a die that this will happen? If we flip a coin, that this will happen. I got it. Spin a spinner. You know, we did one thing. We figured out the probability of the one thing. When we're talking about a compound event, we're talking about doing a couple things, such as what's the probability of getting a heads and a 6 if I flip this coin and roll this dice. This one here, what would be the probability of me getting a D and not a red when I will spin this spinner and pick a marble out. So compound events, again, deal with probability of an event, but there'll be two or more events. We're really only going to focus on two, not three. You know, we don't need to get too crazy with it in 6th grade here, but bottom line is compound event, as you would assume, the word compound usually means multiple, more than one event. We will be figuring theoretical probability for all this stuff here. This is not an experimental probability lesson here, just theoretical here today. So not running trials or anything like that. So everything here is theoretical. So that means if you forgot, hopefully you didn't forget, write it down if you need it, but we're talking number of favorable outcomes on top. And then number of total outcomes on the bottom. This formula, or whatever you want to call it here, will drive all our action today. Same deal as 813. One of the first things I always like to do first is you need to know how many total outcomes are on the table. So that's what we're going to work on. We'll use tree diagrams and counting principle to help us figure that piece of information out here. And then once we know how many total outcomes there are, we will determine how many favorable outcomes there are, and that will represent our final answers here. So let's look at number 1. Okay, looking at page 277 over here. And number 1 says toss a coin and roll a die. Or dice, whatever you want to call it. Dice. One. Okay. Right. Die is a singular dice. It is the official word of it. One die. Dice is just a die. And if you got 2 of them, those are dice. Dice is the plural form of die. But that is true. That is true. So again, it feels awkward to me too to say die, but that's why I call it dice. But officially, I'm rolling a die. I'm rolling 1. So, but that is true. That is truth. So, but whatever you want, it doesn't matter. Guys, shh, too much talking. Too much talking. So, what do we need to do? We're going to make a tree diagram, and then we're going to talk about the counting principle. True, but let's talk about tree diagrams first. And how do we make them? Because we're going to make a number of them today in this lesson. So a tree diagram is a way to show all the total outcomes that are available to you. And I'm going to set it up here. Again, we got 2 events. So the first thing we're going to do is toss a coin. So what could happen when I toss the coin? Right. So what I'm going to do here is I'm going to write both those things out because there they are. I could get a heads or I could get a tails. All right. Now I got to roll the dice or the die. What could happen when I do that?
You get a 1, 2, 3, 4, 5, or 6.
I could get a 6. So let's pretend I flipped the coin first and I got a head. Right? There it is there. And then I roll the die. And like you said, what could happen next after I get a heads and roll the die? I could get a 1, a 2, a 3, a 4, a 5, or a 6. Okay? On the other hand, I could have flipped the tails. And then when I roll the die, what could happen? Same situation could happen. I could get a 1, a 2, a 3, a 4, a 5, or a 6. This is a tree diagram representing this scenario where what I do first is I just write those down, but these, we call them branches, hence the term tree diagram. Hence the term tree diagram is we draw branches out representing all the outcomes of what could happen next, right? And if I listed out all the outcomes here, guys, what's the issue? Me either. I don't know why we're all staring at the door. If I wrote down in table form all the different outcomes that are available to me, I could get a heads and a 1, I could get a heads and a 2, a heads and a 3, a heads and a 4, a heads 5, a heads 6, or I could get a tails and then a 1, tails 2, tails 3, tails 4, tails 5, or a tails 6. Those are all the things that could happen when I flip a coin and roll a die. How many different outcomes are there available to me? There are 12 things that could happen. So that's, again, when I start answering some questions here, and I'll ask you some questions about this, that's going to, again, be my driving bottom number here for everything I do. And I can see these 12, again, you can write them in table form. This is what we call table form here. You first want to build a tree diagram, but you can also just count up the branches. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can see them all out there. So now I can answer some basic questions here, where if I said, what is the probability of getting a heads and then rolling a 2? 1/12. Right, because how many of those are winners? Just one. That's the only winner right there. I got to get a heads 2, so I would say the probability of getting a heads and a 2 is 1 in 12. What if I said the probability of a tails and odd number? What's the probability of that event occurring? 1/4, but before that it would be 3/12. And again, a tails and an odd, so you're asking yourself, what are my winners? Well, tails 1, that's a tails and an odd number. Tails 3, that's a tails and an odd number. And tails 5, that's a tails and an odd number. There are 3 winners out here of the 12 possible things that could happen. And yes, 1/4 is what the final answer would be. We always simplify just like yesterday. What if I said the probability of not heads, not 4? What's the probability of not heads, not 4? 5/12. What do we all think? Not heads, not a 4. 5/12 it is. So again, you need to just pause, and again, you guys rightly did. If I rewrote it, I could have wrote it this way too. The probability of getting a tails and a 1, 2, 3, 5, or 6. These are exactly the same thing that I wrote here. One and the same. So we covered this not concept before yesterday. I think you guys understood it, at least going through the homework. You seemed pretty good about it. But these are one and the same thing here. So I don't want heads, so that means all these are losers. I want not heads. And then I don't want a 4. So that's not what I want either. What am I left with here? 1, 2, 3, 4, 5 of the 12 are winners using my tree diagram here. Okay? I'm going to show you the counting principle. Again, we're going to use both of these here. Tree diagrams versus counting principle. Both of them accomplish the same thing. All right, both of them do accomplish the same thing. But the counting principle can leave you just a little bit short of info sometimes, and you have to be able to understand kind of what your outcomes are going to look like in a tree diagram here. But the counting principle deals with, we talk about when I talk about I'll write it out here so you can write it out too, the counting principle, how this works here. And it's pretty slick, to be honest with you here. But what I do is the number of outcomes of event 1 times the number of outcomes of event 2. And honestly, I could continue this. Like if I said flip a coin 3 times, what's the probability of getting heads, heads, and heads? Heads all 3 times. I'll show you. So, or I could say flip a coin 5 times. What's the probability of getting heads, heads, tails, heads, heads type of deal here? And I'll show you how this works. But there's no limit. I mean, we're talking compound events here for the most part. We're dealing with 2 events here. But all I need to do is multiply the number of outcomes of each singular event times together. When I'm done, that will give me the number of total outcomes. And of course, we know that number is magical and critical to what we do. That's the bottom number of my fraction up here. I need to know how many total outcomes they are. So if I go back to my situation we just did, flipping the coin, how many total outcomes are there? 2. I could get the heads or the tails. And then when I roll the dice, how many total outcomes are there for that? 6. So I multiply the number of total outcomes of what could happen when I flip a coin times the number of total outcomes of what could happen when I roll the die. 2 times 6 gives me a grand total of 12, which we know is correct. When we built the tree diagram, we were able to visually see all 12 of those outcomes. But the counting principle gets me the same thing here. It tells me there's 12 total outcomes. So what do we use them both for? The tree diagram, again, is much more helpful for lower level learners. Like when we were I'm not saying you're low level, and I'm not saying you're low level in 6th grade either, but we're still on the lower level of where we are in the probability statistics game of things. Tree diagram is awesome to visually see everything that could happen. And you can kind of list it all out there. And the tree diagram has great purposes. I mean, if you're just flipping a coin, rolling a die, a little spinner.
So the counting principle is just to get the denominator?
Correct. Right. But again, this can be helpful here, at least in this case, because you should understand, again, especially there's only one 6 on a die. There's only 1 tails on a die, so it works great here. And building tree diagrams is perfectly fine with some of these scenarios. But if I got to you and started saying this scenario, say if I said, pick a card from a deck, right, and roll a die and pick a letter A through M. Well, trying to build it, you don't necessarily have to write this out here, but this, I'm not saying we couldn't make a tree diagram of this scenario here, but it would take forever, because if I say pick a card from a deck, well, there's 52 cards in a deck, and then rolling a die, there's 6 more outcomes, and a letter A through M, A, B, C, D, E, F, G, H, I, J, K, L, M. There's 12 of them. And then if I want to know how many total outcomes there are, just to speed this up, times 6 times 12, that is 3,744 total outcomes. Yikes. So, I mean, could I make a tree diagram of that? I guess, in theory. But how long would that take? Well, that would take eons of time. That would
Wait.
take
Eighth
A,
round,
B.
13.
Oh, okay. I was wondering if I got that wrong.
Yeah.
Okay.
So it is 4,000.
Yeah.
56.
Right.
Yeah.
Let's go.
Right. Even more. So you can see where the tree diagram kind of runs out of its usage here long term here, and as you continue in your life here, probability stuff going in 7th, 8th grade, we are going to run into scenarios that have hundreds of outcomes to them, and building a tree diagram is simply not a practical way to go about doing it here. So again, there's some value in the tree diagram, yes. Especially where we're at here in 6th grade, we will have to build some tree diagrams. Again, outside, when we get into the last 2 lessons, they're not required at all, and we're gonna be doing something different anyway with probability. But we'll use them both. We're continuing to utilize tree diagrams for now. They have benefits. You guys haven't had a lot of, as far as I know, you've had all of, well, including yesterday, all of 4 days training in probability to this point in your life. So to say you're seasoned and experts at it would probably not be correct. So we will continue to utilize tree diagrams at this point so you can continue to visually see what's going on. But next year, we'll continue to make some tree diagrams, but we're going to start reducing how many we do, and we're going to shift you more to the counting principle. So does that all kind of make sense here?
Yeah.
Again, counting principle is better in the long run. Tree diagram is better to visually see what's actually going on. So both have their pros and cons here, to be honest with you. One is neither better or worse than the other, but it's just, as you understand, the tree diagram has its limits. It wouldn't make sense to build a tree diagram with hundreds of outcomes. You would want to use counting principle. Okay, so try number 2 on your own. I want you to build a tree diagram here. It shows me this spinner here, A, B, C, or D, and then I got these 3 marbles in the bag, a blue, a green, and a red. So what would my tree diagram look for that? And then check it, double check it, use the counting principle afterwards to verify. Build the tree diagram of all the outcomes. If you want to list them in a table form, that's fine, but then verify your information with the counting principle. So make a tree diagram, show me all the total outcomes available, use the counting principle to verify.
Okay.
I'll give you a moment here, and then I'll build it up. Truth be told, I mean, if you spin the spinner first, then pick a marble, great. But if you chose to pick the marble first and then the spinner, it doesn't really matter in this case here. So if for whatever reason you decide to list the marbles first, blue, green, red, and then build your little diagram, I'll build them both real fast. So I'm going to build them both, and I'm going to show you that it's one and the same. But if I spin the spinner first, I can get the A, the B, the C, or the D. Right? And now, my second event here is pick the marble. And I got 3 marbles. I could get the blue marble, the green marble, or the red marble. So I could spin an A, then get the blue marble, the green marble, or the red marble. I could get a B, blue, green, red, blue, green, red, blue, green, and red. There are 12 total outcomes here. I could have built it the other way, where I'm going to just, if you did, just prove to you so you can see it for yourself. But pretend I did the marble first. I could get the blue marble, the green marble, or the red marble. And then I go to spin the spinner. A, B, C, D, A, B, C, D, A, B, C, and D. So in this case here, you need to start wrapping it up, Damien. You too. You need to end it at this point here. Consider the warning issued. What I'm trying to illustrate to you here is it doesn't really matter with in this case, these events, because what happens when I spin the spinner has absolutely no bearing at all of what's going to happen to me when I draw a marble out. There's no connection between those two events. But whatever one I did first or second, as long as I do them both, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, both ways I end up with 12 total outcomes. Agreed? If I use the counting principle to check it, when I spin the spinner, there were 4 total outcomes, multiplied by when I pick a marble, there are 3 total outcomes there. One way or another, I'm going to get 12 total outcomes here. Okay. One more. I better help you with that one, but try number 3 on your own. This time, you need to kind of dictate yourself how you want to do it here. It says make a sandwich of 5 different types of bread and 2 different fillings. So, again, 5 different types of bread. How are you going to represent that in your diagram here? And then 2 different fillings. So, it's kind of up to you to kind of figure out how your diagram's going to look here. And there's plenty of ways of how this could be done. If I built a tree diagram, I could just simply, I could think of names of bread. I could be like pumpernickel and wheat and rye, and I could name my own breads. Or if I don't even know 5 types of bread, very conceivable, I could just call them bread 1, bread 2, bread 3, bread 4, and bread 5.
I did in the middle an F for filling and then just 1, 2, 3, 4, 5.
Yeah, there's a couple ways you could do that. I could list out 5 different types of bread with 5 different letters: sourdough, wheat, rye, pumpernickel, focaccia. So there you go. Then I would have 5 different letters and stuff like that. But then the fillings, again, I could have lettuce and tomato, or I could just call them filling 1, filling 2, right? Whatever I want to call them there. But what you should come up with, how many total outcomes are there here?
10.
There are 10. Okay, let's look at number 4. And I'm going to make this a little clearer for us. But this time we have 3 different things going on here. We're going to build a tree diagram. We're going to use counting principle again. So I'm going to put colors to everything here to make it somewhat easier. So they say 4 shirts. I'm going to say you got a green shirt, a blue shirt, a red shirt, and a yellow shirt. Okay? Shirts. And pants. I'm going to say we got black pants and white pants. Pants. And then sweaters. I'm going to say we got an orange sweater and a purple sweater. Okay? And we want to build a tree diagram here. So I'll give you a moment. I'm just curious to see how you see this through here. But how many total outcomes are there, and what are they all? Build a tree diagram here. Anybody have an idea how that's going to work?
What does that say on the right? Does it say
Sweaters.
sweater?
Put together an outfit from a selection of 4 shirts, 2 pants, and 2 sweaters. A couple of you are giving it a shot. A couple of you are curious to see, what do you think your tree diagram is going to look like with 3 outcomes? We did one with 2. But now I got 3. How's that going to look to us? So I would let's just start with the shirts. I'm just going to go right down the order. So the first thing I'm picking is a shirt. How many options do I have? 4. I could get the green shirt, the blue shirt, the red shirt, and the yellow shirt, right?
Yeah.
There they all are. So now let's move on to the pants. What could happen there?
You got black or white?
I could get a green shirt with my black pants or my white pants. I could get the blue shirt with my black pants and my white shirt. I could get the red shirt with my black pants and white shirt. And I could get the yellow one with my black pants or my white shirt. At this point here, you agree with all this to this point?
Yeah.
Now, we're not done. Now I got to get a sweater too. So I could get a green shirt in my black pants, but then I could have either an orange sweater or a purple sweater. I could get the green shirt with the white pants, and then I would have either an orange sweater or a purple. I should have put a P here. I think I put an R. Right? And once again, I could get blue shirt, black pants, orange sweater, purple sweater, orange sweater, purple sweater, orange sweater, purple sweater, orange, purple, orange, purple, orange, and purple. So if I count out how many total outcomes there are, I could have the green shirt, the black pants, the orange sweater. I could have the green pants, the green shirt, the black pants, the purple sweater, this one. I could have the green pants, the green shirt, the white pants, the orange sweater, the green pants, the green shirt, the white pants, the purple sweater. 1, 2, 3, 4. And ditto over here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And I'm not going to keep writing them all out here. But how many total outcomes are there? How many outfit combinations could I make? There are 16 outcomes here of what could happen if I pick out one of 4 shirts, one of 2 pants. And if I go to the counting principle again, the shirts, there are 4 total outcomes, times the pants, which there were 2 total outcomes for, times the sweaters, which there were 2 outcomes for. 4 times 2 is 8. 8 times 2 is 16. There are 16 total outcomes available to me here. So when we get into diagrams that have 3 things, you can see how I kind of built the tree. Again, I got the first scenario here, then I made my thing. If I just said pick a shirt, pick a pair of pants, I would have 8 things that could happen. We saw them all here. But then to build that next level here, I need to go off my second level and build another, basically, tree on top of a tree. Hence the branches one more time.
On the test or quizzes, will we have to use the trees, or can we use the?
You'll be required to make at least one tree diagram. And then, yeah, just again, it won't be an overly complex diagram, but then everything else, unless I explicitly say I want a tree diagram, then you can do whatever method you
So
feel
we
is
probably
best
won't be
here.
forced to make a tree diagram of one of these.
No, I'm doing it so you can kind of see, 1, how it's done, and 2, you're able to visually see all the different outcomes that are going on here. And if you can see this, it makes it a lot easier to understand, I think, for you. So, no, we're not going to go to this depth forever and ever and ever. It's just, I'm trying to make it real understandable for you guys here. Okay? Good with that?
Yeah.
Okay, now we need to talk about independent and dependent events here. So, independent events. And this is always a little challenge. We covered this concept last year, independent versus dependent events here. In independent events, the first event has no bearing on the second. And I'm just going to write them both out, and then we'll talk a little more about what they mean. Dependent events, complete opposite. What happens in the first event directly impacts the second event. Okay.
How did you do that?
Now, all the events that we've covered at least today and yesterday here, are independent events. I guess, again, when you're talking, you need two or more events to either be independent or dependent. So you need two or more things to happen for this to be a consideration. But the things we've dealt with, our coin and dice and these things here, these were all independent events. Because whatever happened when I flipped the coin had no bearing on what's going to happen when I roll the die. Whatever I spin here has absolutely no bearing whatsoever on what's going to happen when I do this. So let's look down here to this part here. And what they're saying here is pick a marble from a box. Okay, and they say we got 3 yellows, 2 whites, and 1 red. Okay, and 2 things are being asked. 1, they're saying if the choice is replaced, and B, if the choice is not replaced. So one more time, we're going to be building a tree diagram here. So I want you to build, it won't take that long. There's really not that much, I promise you. But what I want you to do is build a tree diagram. Assume I'm going to pick a marble. I'm going to put it back in the bag, and then I'm going to pick another marble. So what could happen the first time? Kind of. How many marbles are there?
You could get 3 yellows.
Right, I could get that yellow, I could get that yellow, that yellow. I'm going to change this just a little bit. Let's call this 2 yellows, okay? Just to reduce our diagram size a little bit here. So what could happen? One of 5 things is going to happen, right? I could get this yellow, or I could get the other yellow. I could get this white, that white, or I could get a red. One of those 5 things is going to happen, right? So I pick my marble. I go, oh, okay. And then I put it back in the bag and I pick again. So what could happen the second time?
You could get a yellow.
I could get the yellow, the white, the other white, or the red. All 5 of them are there, right? The yellow, the white, or the red. 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 So, how many total outcomes are there here?
20? No, 25.
There are 25. Counting principle would tell me the same thing. First one I pick, there's 5 total outcomes. When I pick again, all 5 marbles are there. Still, once again, 5 total outcomes. There are 25 total outcomes. Agreed with that? Right. And this is an independent event. Whatever happens the first time, there's 5 marbles. I got an equal chance to get any of them. Throw it back in the bag, pick again. Once again, there are 5. Whatever I draw the first time, it doesn't matter because they're all there. But there's 25 things there. And I could ask any, if they say, what's the probability of getting a red and a yellow? Let's try and figure some of those out. So what's the probability of getting a red and a yellow? Red first, yellow second.
2/25.
Right, because remember, I could get, first I gotta get the red, so I could get red, or I could have pulled that other. It doesn't really matter which one I pulled, they're both yellow there. So in this case here, if I said the probability of getting red then yellow, you would say 2/25. Because there's my winner right there. What if I said the probability of getting a white and then another white? White.
Oh, wow. 8/25? No. 2/25.
4/25. Where are my winners? White, white, and white, white. There's my white, whites. Doesn't matter which white I get, but I could get, these are my 4 winners right here. The probability of getting a white followed by another white is 4/25. 4 of the 25 total outcomes are white, white. right? Right. So this is an independent event. Now, same deal here. Same situation. 2 yellows, 2 whites, 1 red. This time, we're going to pick a marble, but we're not going to put it back in the bag. Whatever we pull, we're going to just set it aside. And then we're going to pick another marble. So, what could happen the first time?
You could get 2 yellows.
I could get the yellow, the white, or the red. Right? And I should, again, probably just put somewhere, just when you're looking at your notes, pick a marble. This is what we did here. Put it back. Pick again. This is what we just did up here. That's what this tree diagram has represented to us here. That we picked a marble, we put it back, and then we're picking again. So this time here, we're pick a marble. Do not put it back. And then pick again. Okay. So this time here, again, same 5 marbles, 2 yellows, 2 whites, 1 red. Nothing's changing there. First marble I pick is one of these 5 here. And assume I pick this yellow marble. Now I'm not putting it back. So what could happen when I pick the next marble? What are my choices?
A yellow, white, and red.
Right. Notice how the diagram changed a bit. Because why did it change? Well, if I pull this yellow marble out instead of the side, what's still in the bag? There's only 4 marbles in the bag now because that yellow marble's not in the bag anymore, right? It's gone. So what's left in the bag? Only one of the yellows this time. The 2 whites are still there, the red is still there, but one of the yellows is no longer an outcome for the second pull because I didn't put it back in the bag. And similar, if I get the other yellow, I could get that 1 yellow, both whites are there, the red is still hanging around. The white here, again, both yellows now are in the bag. The other white is in there, and the red is in there. If I get this white, both yellows, I could pick second. I could get the other white marble, or I could get the red marble. If I pull the red marble out first, what's in the bag? The 2 yellows are in the bag, and the 2 whites are in the bag. How many total outcomes are there?
But don't you keep the one in the bag the whole time?
There's 20 outcomes this time.
And then you keep it out, and then you pick it up. I know, so once you just keep taking those ones out.
So, and again, think it through. Using the counting principle, how many total outcomes were there when I picked that first marble?
4.
No, there were
Never
5.
mind.
But when I picked the second marble, how many outcomes are there?
4.
4. Because again, notice the difference here. If I don't put that marble back, it changes the amount of outcomes that are available. To me, the second time here, only 4 marbles in the bag the second time, right? You pull one out, you don't put it back, how many are left in the bag? All right? So, same questions here. What is the probability of me getting a red followed by a yellow this time? Right. Same deal, where I do not put it back. 2 20ths. There's 1 winner. Or I'm sorry. That's not what I wanted. Wrong one. I want it over here. Right. 1 right here. And 1 right here.
Oh, I get it now.
So 2 winners of the 20, 1/10. And again, contrast that to what we did before here. When I put it back here, 2 25ths. What about going white-white? What's the probability of that happening?
1/10.
Same deal. So there's a winner, and there's the winner. 2 20ths once again, 1/10. But white-white, compare that to what we did before. Well, there were 4 winners before when I put it back in the bag because, again, it's back in the bag. I can get either of the white marbles. But if I don't put it back, that changes how many, it's no longer 4 anymore this time. There's only 2 winners. The odds of that happening if I don't put it back are less. Right, there's only 2 winners this time. Probability of white, white, 4 and 25. Probability of white, white, 2 and 20. If I put it back or don't put it back, it changes the probabilities of what could happen. This is an example of a dependent event. Whatever happens the first time, whichever of those marbles I pick has a direct impact on what's going to happen the second time. If I pick a yellow, there's not as many yellows. So that changes the probability of me getting a yellow, yellow or a white, white. The odds of me getting white, white are better if I get a white marble and put it back in the bag. If I turn it into a decimal here, this is 16%. I can tell you that right now. 4 divided by 25 is 0.16 or 16%. But if I don't put it back in the bag, 2/20ths, this is 10%. Not as likely to happen. And you would expect that to be the case. If I don't put one of the white marbles back, the odds of me getting white, white are probably going to drop, right? And they will drop from 16% down to 10%. So this is a dependent event. Whatever happens the first time will directly change the outcomes that are available to me to the second time. It will also change the probability of what's going to happen in the event. Make sense?
Yeah.
Okay. So I'll give you one here. I'm going to keep it pretty short here. I will let you decide if you want to make a tree diagram or not. It's not the worst idea here, but I'm going to say, just create a scenario here for you. I'm going to say just shapes. I'll say you got a star, a circle, a square, and a rectangle. And run it both ways here. First, independent. Grab one, put it back, grab again. So grab one, put back, grab again. And then same deal later on here. Grab one, do not put back, grab again. So couple things here. Let's say, what is the probability of me getting a star, then not circle, and the probability of me getting a 4-sided shape, and not a 4-sided shape. That'll let you think about it for a little bit there. So I would suggest building a tree diagram of both outcomes, to be honest with you, and compare and contrast them so you can quickly find your winners visually. It's not going to take that long to build a tree diagram of this scenario. It won't, but this is kind of you need to think it through. You'll probably want to see all the visual outcomes in front of you here to answer this type of question here. Maybe not, I don't know, but again, this is designed to build a tree diagram. If you think you can do it without, it's your choice. Ultimately, I just want the right answer. But I'm going to be building tree diagrams for both of them. And again, figure this out, both independent and dependent. Same question for both. Star has 5 sides to it, by the way. 1, 2, 3, 4, 5. So, lest you wonder. Your homework here, draw a tree diagram and use the counting principle. I only want you to build a tree diagram for definitely not 5 and 6. And all they're asking you is how many outcomes there are, 1 through 6 here. Only 7, 8, and 9 want actual probability type answers. So 1 through 6, you're only figuring out how many total outcomes there are, period, end of discussion. So 5 and 6, why don't we just say, build the tree diagram for the first 3, use the counting principle for the last 3. So numbers 1, 2, and 3, I'm looking for a tree diagram in your homework, right? There's 9 problems here. Write this down or whatever you want to do here, but make a tree diagram for numbers 1, 2, and 3. Use counting principle for numbers 4, 5, and 6. Does that make sense? Right. 1, 2, and 3 are smaller. 5 and 6 are definitely bigger. Making you make a tree diagram would be cruel and unusual punishment for those two. And 7, 8, and 9 is the independent, dependent events. They got the bag, 5 red, 3 blue, 2 white. That's a lot of outcomes there. I'll let you decide how you want to approach that, but you should have 2 answers for 7, 8, and 9. One answer is the probability of the independent event. The second answer will be the probability of the dependent event. One answer is if I replace the thing back in the bag. The other answer is if I don't. Okay? We all clear on the homework here, what we got to do? 1, 2, and 3 tree diagrams. 4, 5, and 6 counting principles. 7, 8, and 9, 2 answers. One for put it back in the bag. Second answer for don't put it back in the bag. Okay. So I'm going to build mine here. I'll say a star, a circle, a square, and a rectangle. If I put them all back in the bag, all 4 of those are there for the taking again. So any of these things could happen. 16 total outcomes. Yes?
Yep. Yeah.
We agreed with that? Okay. So if I said the probability of getting a star followed by not a circle, how many winners do I got? 3. Star star is a winner. Star rectangle is a winner. Star square is a winner. Star circle's not a winner because I said not circle. 16 total outcomes. 3 and 16 to get star followed by not circle. If I said a 4-sided shape, that's the square and the rectangle. Those are 4-sided figures, right?
Yep.
Right, so those are out right off the bat here. Followed by not a 4-sided shape. So square star is good, square circle is okay. That's, no, I said not a 4. And then a rectangle star is good, a rectangle circle is good. I got 4 of the 16, that's 1/4. I should come up with that. A 4-sided shape, what are my 4-sided shapes? A circle's not, a star's not, a square is, and a rectangle is. So there's what I want to have happen first, get a 4-sided shape. That means these are out. Stars and circles are not 4-sided shape, but then not a 4-sided shape. So that is, and that is, I said not a 4-sided shape for the second one here.
Okay.
So now the second time, I'm basically saying I want the circle or the star,
Oh, yeah.
right? Not a 4-sided shape the second time, right? See how that worked? All right, and now same deal, dependent here. Starts out the same, the star, the circle, the square, the rectangle. But if I don't put it back here, well, I could get the circle, the rectangle, the square. I could get the star, the rectangle, or the square. I could get the star, rectangle, circle, the star, the square, or the circle. And again, how many total outcomes do I have this time? 12. So same two questions. Probability of getting a star by not circle. There's one winner. There's one winner. 2 of 12. 1/6. To get a star, not circle. And then the other one, the four-sided shape first. So that's gone. That's gone. Followed by not a four-sided shape. So square star is okay. Square circle is okay. Rectangle star is okay. Rectangle circle is okay. That would be 4 of 12. Odds are increasing this time. Before it was a 1 in 4 chance, but if I don't replace it, now I got a 1 in 3 chance of that happening there. 1 in 3. Odds have improved in that scenario there. So again, tree diagrams, I definitely recommend them for some of them here. Again, they got their time and place here. They are very helpful, especially with things like this that you got to kind of really ponder it out for a second there. I don't know. Did anybody not do a tree diagram and get these right answers?
I got the first one that said tree diagram.
Yeah.
I made
Yeah. I'm leaving it up to your discretion here what you need to do. Like I say repeatedly to you guys, as long as you get the right answer, I love how you did it. But again, you will explicitly have to make probably at least one tree diagram on your quiz and test. But there'll be options to make more. I'm only going to grade you on one, though. So, well, I guess no time, but so it goes.
New longest video for us, by the way.
Like and subscribe.
Thanks, Brooke.